Okay, so chapter 4, we're going on with in that topic about the atom, and we talked most of what we've learned about the atom. They discovered that the atom has an electron, and we had more detail about the inside of the atom. That the nucleus is very small. Almost all the mass is in the nucleus, and it's positively charged. Now we're going to start talking more about the electrons, because the electrons really are kind of where it's all at, because that's where all the bonding takes place. Whenever there's a chemical reaction, it involves the electrons. The inside is just kind of along for the ride. So what we want to cover in this first section is we're going to find out what is the relationship between the wavelength, the frequency, and the speed of an electromagnetic wave. We're going to come up with an equation for that we're going to be using in this chapter. We're going to talk about light's dual nature that it has. And then we're going to talk about something called the photoelectric effect. You have all experienced it, but you probably didn't know exactly what was going on with that. We're going to talk about that. That helps us to understand a little bit more about the atom, and especially the electrons. And then we're going to talk about kind of like our first model of the atom that gives us a more detail, not only about the nucleus, but we now have detail about the electrons that are orbiting the nucleus. Okay, so let's first talk about light, because all that we've learned about electrons really comes from how it interacts with other matter and the light that it gives off. So electrons can cause light to be given off, and we're going to talk about that. Now, if you remember back from physical science, we talked about the electromagnetic spectrum, and the electromagnetic spectrum was on that chart over there. We'll have one here in a moment on one of these slides. But they all exhibit wave properties. Now, one of the things that we probably need to remind ourselves about is back in physical science, we talked about, is light a wave or is it a particle? And they had people that supported both positions. And by the time we got to the end of the 1800s, the predominant belief is that light is made out of waves, okay? And so that kind of fits with what we're seeing right here. All the different forms, like gamma rays, cosmic rays, X-rays, microwaves, ultraviolet waves, you name it, are all part of this electromagnetic radiation, part of the electromagnetic spectrum. And here is maybe kind of shows this whole spectrum right here. The shortest wavelengths are gamma rays. The next shortest ones are X-rays. They're also the most powerful ones. They can go, like gamma rays can go through just about anything like it's not there. X-rays can be blocked. We know that if you've ever seen an X-ray of somebody's broken wrist or something like that, you know that the bones can block some of the X-rays. And so as you go this way, it's easier and easier to block the waves. Ultraviolet, it doesn't go through us, but it does affect the skin, and our body can either tan because of that or burn because of that. But UV is a good thing. We can even use UV to destroy bacteria with ultraviolet. I noticed what was in the Menards flyer that we regularly get. They had a UV wand. It's battery operated. You just open it up like this, and you can shine it over surfaces that might be contaminated with bacteria, and it'll kill them just by with UV. And then after ultraviolet is the part that our eyes are sensitive to, what we call visible light. Our eyes primarily can only see 3 colors. It's the same 3 colors that a TV makes color with, red, blue, and green. And it's just different amounts of each that can make us have all the probably millions of colors that you and I can detect just with just those 3 colors. We don't really see brown. It's just a mixture of the other colors that our brain interprets as brown. Then beyond visible light, we have infrared. That's more has to do with heat energy. Your body is emitting infrared right now because you have not, I was going to say because you haven't attained room temperature, but no, even at room temperature, it emits radiant energy. Infrared. And then we have microwaves, and then beyond microwaves, we have all the different kinds of radio waves that we use, like for television and stuff like that. So all of that is the entire electromagnetic spectrum. Now, all these waves, because they're waves, we have wavelength. And the symbol for wavelength is the Greek letter lambda. The way I write it is I draw a slanted line like that, and then I prop it up. Okay? So that's the Greek letter lambda, and it represents the wavelength, and it's just the distance between 2 corresponding parts of waves. Most people will define it as, it's like between one crest and the next crest, or one trough and the next trough, or something like that. But that would be the wavelength. It's a distance. So this one is measured in meters, because it's a distance. The next property of waves is that it has frequency. Now here it looks kind of like a cursive V. I think it's the Greek letter nu. It would make more sense to, I think, most of you, and you would have less trouble with it being confusing if you would think of it maybe as an F for frequency. Okay? Probably back in, my guess, in physical science, we probably put an F there for frequency. And frequency is how many somethings are happening in a second. That's the whole idea behind frequency. How many somethings. So it's like somethings, we'll say 1 over second, somethings per second. The SI unit for that is actually Hz. Hz. It's named after somebody, again, called, I don't know what his first name is, Helmholtz Hertz. These are German names, so they sound a little strange to us, but we're not German, that's why. So a hertz is the same thing as something per second. Now, frequency and wavelength are related to each other, and the way we've discovered the relationship that exists, that we learned that velocity is frequency times wavelength, but we're talking about electromagnetic radiation. So it's going to be the speed of light. C is the speed of light. It's measured in meters per second. Interestingly, the speed of light has, the way we define it has changed. Originally, the meter was defined, and then they measured how fast light travels per second. Obviously, had to define a second. How fast light travels per second. But then it was a decimal, also had decimals with it. So I don't know how long ago they did that, probably in the last, 10 or 15 years. They decided they were going to kind of switched the thinking around. Let's say that the speed of light is exactly a whole number. What they did is I think they took the speed of light and dropped off the decimals or rounded, whatever. I don't know what they did exactly. They said it was now the speed of light is this. So that means that the meter has to change slightly in length, right, to compensate for that, dropping off the decimals. So now the speed of light is defined as an exact number, not a decimal number, and the meter is now defined in relation to that instead of the other way around. I guess it's more convenient. I don't know. To me, it doesn't make any difference to me because I don't usually have to work with those numbers. But I'm sure there's some fields where that was a lot. And I'm sure it was a discussion that went on over a period of times that they met, because they don't meet all the time. They only meet maybe once a year at the most, maybe once every other year. I don't know. And they talk about through these things, and there's a better way maybe of doing some things, and they'll switch if the whole conference or whatever they call their group thinks it's a good idea, then they'll switch stuff around. That's kind of happened way back in, what was it, the 1970s, 1980s, when they start kind of formalizing some of the names for units. Like, for instance, when I was in high school and college, and actually the first part of my teaching career, the temperature scale that most of the world uses, we call centigrade with a capital C. Well, they decided, well, let's name it after the guy who did a lot of work with temperatures, made it come up with a scale, and it was Anders Celsius. Let's just name it after him. So now it's called Celsius, but it originally wasn't that. He didn't name it. He came up with centigrade, but now that he's dead, we can do anything we want to without him complaining. And so we changed it to Celsius. So that's that's what they do. They make decisions like that. So the speed of light is equal in meters per second is equal to the frequency times the wavelength, as it shows there. C equals wavelength times frequency, or if you want to change that V, that Greek letter nu, to an F, it probably might mean more to you than it does the V, because the V to me looks like velocity, which is also meters per second. Which that would really be confusing when this is meters per second, and you're thinking about that as being meters per second. So that's why I think F would probably be a better letter to use right there. So C is the speed of light. We have no reason to believe at the moment that the speed of light is changing, but we're wondering if in the historical past, if the speed of light always has been constant. There's some things that we know that from our studying of them that are connected to the speed of light. Like radioactive decay somehow is related to the speed of light. I don't know, I'm not sure how, but it is. But there's some things that indicate that the radioactive decay today is not at the same rate as it was in the past. It was much faster in the past, which would mean the speed of light would have to have been faster, which would kind of help to explain the fact that how could light have traveled from distant galaxies to the Earth, and we see them right now. If you want to just explain it in a purely scientific way, our only other choice as creationists is that, well, the same God that created these galaxies created the light already going in all directions so that everything experiences it right now. You didn't have to wait for thousands of years for it to arrive. I'm not sure what's the right answer to that question. So wavelength is just how far from like one crest to the next crest or one trough to the next trough. So like the top one has a long wavelength, the next one has a short wavelength. But according to that equation, and I'm going to use frequency and wavelength. I'm going to use those letters so that you're thinking like I want you to think. At the moment, how are frequency and wavelength related? Our frequency? Yep, you're looking at the right place, Gracie. They're what?
Direct, indirectly, indirectly.
These two times each other is a constant.
Inverse.
Inverse. It's an inverse proportion. Okay, that's that one right there. A times B is a constant. Okay? So frequency and wavelength are inversely proportional to each other. If the wavelength increases, then there will be fewer waves that go by, right? If you think about you're out in the ocean or along let's say you're standing on a pier and the waves go by, if you have long wavelengths, there will be fewer of those that will go by. So the longer the wavelength, the lower the frequency. Or if you have little tiny waves, that's really entertaining you, isn't it? Okay. If you have really tiny waves, like ripples are really tiny waves, a lot of those will go by in a second, won't they? As opposed to like ocean waves that have really long waves. So they're inversely proportional to each other. Okay, so when certain frequencies of light strike a metal, electrons are emitted. Okay, now we're going to start into the topic of photoelectric effect. Just for a moment, I'm going to think what that word was. Photoelectric effect. So here's what it's saying, is that if you have a bare piece of metal, not contaminated, or, not dirty on the surface, it's a clean piece of metal, that there are some pieces of metal that when light strikes on it, and it says certain frequencies, not any kind of light, but when certain kinds of light strike on it, it causes electrons to shoot out from the surface. So pieces of metal, atoms that have their own electrons, that when light shines on it, it'll knock electrons away from the atoms.
From the light or from the metal?
What?
From the light or from the metal?
The photon, when it strikes the atom, will cause the atom to shoot out an electron. That's the photoelectric effect. Okay? Now, as it says, it's only certain frequencies, or another way of saying that every maybe kind of metal has its own frequency at which that can happen. It's not the same frequency for all metals. Every metal has kind of its own that does that. Now, to be able to, back to I brought this up that back by the late 1800s, they'd already had, everybody pretty much agreed that light exists as waves. Problem was, they couldn't figure out how the photoelectric effect even works if light is waves. If light was a wave, then any wave should work. And if it doesn't knock off electrons, I just make it brighter. But they found out making it brighter didn't do anything. In fact, we could do the reverse. Even if you have the right frequency of light shining on this piece of metal, it doesn't matter how dim, it's going to knock some loose. It's just that when it gets brighter, it just knocks more of them off. So, waves don't explain that. So, a guy that seemingly he's very smart, but he's now talking about something that seems like totally outside of what we know him for. Albert Einstein said, you know what, you guys, the problem is you guys are thinking light is only waves. You got to think of it as being particles. So he brings back the idea that light exists as particles. That light is actually a particle of, like a photon is actually a particle of light. And each particle is carrying a certain amount of energy. And if it's the right frequency, it's carrying the right amount of energy to be able to knock an electron loose. If it's the wrong frequency, it's not carrying the right amount of energy. It's not carrying it enough. It's kind of like you gave, I always like to, my analogy to that is if you didn't give it enough, the right kind of energy, yes, it absorbs the energy, but the electron can't leave. It's sort of like, I can't put my foot on the next step unless I lift it up high enough, right? If I try anything less than that, I just trip.
So we think that light's particles?
So, yeah, so light exists as particle.
So the light didn't give it enough energy when they turned up the brightness?
So here's where we're headed, and then we'll talk about this more in detail, but is that all of light, all kinds of light are actually carried by photons. Each one's carrying a different amount of energy. And that energy is related to the kind of light it is. So in other words, cosmic ray photons carry a different amount of energy than gamma ray photons. Gamma rays are different energy, or actually they're like cosmic carries the most energy. Gamma rays carry a little bit less energy, and as you go down the scale of that electromagnetic spectrum, each one's carrying a little bit less energy. So you have to have it, and to knock an electron loose, it takes a certain amount of energy to do that. So we need to have photons that are carrying enough energy to be able to pull that off. Now, it turns out that any frequency, any kind of light that has more energy than that also works, but nothing less than that. It's either kind of like an all or none type of thing. And the energy that they carry, we call it a quantum of energy. It's a very set amount of energy. It's not a variable. You know, like this photon doesn't have like a dial on it. Well, this photon will dial it in for a certain kind of light, or we can, and the next time we use that photon, we dial it to it. No, each photon carries an exact amount of light, and only one kind amount of light. It's exact. It's a quantum of energy. The energy is the minimum quantity of energy that can be absorbed or gained by an atom. So that for this atom to be able to knock an electron, they're loose. There's a minimum amount of energy that you have to give to the atom to eject an electron. So here is kind of the idea of the photoelectric effect. You probably, let's see, where might you have one of these at? Well, I know that on my garage door opener, that if I walk in front of the control on the wall, then my light will come on. That is using that idea. I'm bouncing, it's sending out, or blocking light or whatever, you know, it depends on how it's made, but that's an example of a photoelectric effect. We sometimes call them seeing eyes. I mean, they give all kind of names to this technology. But here's basically how it works. Okay, you have an anode and a cathode. The cathode up there, it says, is a metal plate, and then the anode is just like a wire up here. And when light shines on the metal plate, the cathode, then that will shoot electrons out that will be attracted to the anode. So in other words, when the light strikes it and electrons jump across the gap, I'm now completing a circuit, right?
Yeah.
I'm completing a circuit. If you were in
That's the robotics one.
in
with the
robotics, you were
flashlight?
doing that, yes.
Oh.
We had some of those that were doing that same effect, except this would be the original tube type. You were dealing with semiconductors that accomplish the same thing, you know.
Was this the same concept as the flashlight moving around the light flashlight?
Yeah, that eye, you shone the light on it, and then we could measure the amount of current. That is related to that, yes. Now, to keep this going, if you kind of think about it, that metal is shooting out electrons. then it's getting more and more positive, isn't it? Well, it's going to run out of electrons to be able to give away, so we need to hook it up to a battery that keeps supplying it some new ones. And it makes the other side positive so that the electrons, when they're shot out of here, are going to be attracted to my anode. Now, so that's basically how it works. Do you have to be able to explain how it works? Not really. Here is a demonstration, and I don't know if it'll work. It's always a battle each year. Will it work? It's a YouTube video. See if I can make it bigger. No, come on. Well, anyway.
Here, hover over.
This is one of those UV wands I was telling you about. Okay, so I don't know if you saw what it was doing. I'll show it one more time. Let's see. Or will we? Yep. Well, maybe. Come on, go away.
What does that do?
I'll explain how it's made, and then it might make more sense. Okay, so what's happening here is this. Okay, so get it to go away. Okay, I just need my picture back. There we go. Okay, so what they have is if you would take like a Coke can, any pop can, and what you can't see, well, just behind his hand, did you see that little black thing down the bottom? That's one of those foam sanding blocks. So if you just sand all the paint off of it, or all the coating that's off the outside, you'd have just bare aluminum. Okay? Then they have a wire sticking out that's been taped to the side of the can. You can kind of see where the tape is. And it goes out to the left, and on the left they put some Christmas tree tinsel. But it's not the kind you buy today. That's the sad part. I always have wanted to do this, but trying to come up with that, because it was very thin and fine, but it was made out of lead. And I think because it's made out of lead, that's probably, maybe they don't want people touching it all the time, but that's what it was. So they're really fine, and so it's just little strands of metal hanging down there. Now, do you know what he's doing with his hands? He's taking a
Charge on?
Yeah, he's putting a charge on it. He's rubbing it like we talked about in physical science, putting a charge on that rod that he has, and he's touching the tinsel, and they all get the same charge, but when they have the same charge, what do?
Oh.
They repel, they stick out like this, okay? And then he touches it. So what's happening?
Shock.
He's
Well,
taking.
it would if we had put enough on it, but he is acting like a reservoir for extra electrons, and so the electrons are traveling from the tinsel through the wire to the can to him, and he's absorbing the extra electrons. Because you can, I can shock you because you can absorb electrons, right? Now he does it all over again, puts a charge on it, but then he's shining UV light on it. So that means that tinsel is the metal that's having ultraviolet light photons striking the tinsel, knocking electrons off and through the air, and so the tinsel is losing its electrons and becoming discharged.
Is it bouncing off?
Would
They're bouncing off because of the photons?
the photons are hitting it, being absorbed. When the atom absorbs the energy of the photon, it then is using that energy to shoot out an electron away from the atom. Okay, so he's actually discharging it with UV. That's the photoelectric effect. That's what, you just saw the photoelectric effect at work. It's not, now, the device I showed you before is how you could actually make it useful. This is just a demonstration. But that's how it works. So if I could find the tinsel, I could demonstrate this every year, but I've looked online multiple times and not been able to find any that I was willing to pay for. I guess it's maybe, because it,
Pay for it and then use it every year.
well, I know, but I didn't know if I want to pay that much money for it. Because if, I don't remember what it was, but I just thought, my goodness, that's what you want for that thing?
Just get like a pencil and then strip the lead off.
But is the pencil made out of lead?
Yeah.
No,
Not that.
It is made out.
it's not made out of lead.
You got letter in here? Just-
Could keep saying it louder, sooner he'll catch it.
Graphite?
It's made out of graphite. It's actually kinds of carbon.
I've been lied to.
You've been lied to.
We can see them now, they'll
Now,
say lead on.
can you take a piece of lead and write with it? A real piece of lead, metal piece of lead? Yeah, here. You rub on it and it makes lines. So I don't know where, if that's what they started with and then switched over to graphite and still called it lead. I mean, we do a lot of stuff like that, you know, and somebody didn't tell you the whole story, did they?
No one
So once Einstein said, you know, you need to look at this as being a particle of light, then a guy by the name of Max Planck, it looks like Planck, but it's Planck, proposed this relationship between radiation, in other words, the energy of a photon, and the frequency. Now here they're using the V again as frequency, okay? So I could write it as E equals HF if you wanted to. The amount of energy carried by a photon is directly, notice that they're on opposite sides of the equal sign. Or if I take and solve this for H, which is Planck's constant, I have E divided by F. What relationship is there between energy and frequency? If it's one divided by the other is a constant.
Direct?
It's a direct, right? So if one divided by the other is a constant, it's a direct relationship. So this actually is a constant. And obviously we're going to call it Planck's constant, okay? Or Planck's constant. And there is the number that he came up with, 6.626. Usually we just say 6.6 times 10 to the 20, negative 26. But that's the number of joules, seconds. That's the what the constant is, because this is measured in per second, right? This is measured in joules, or energy. So we need a constant that will give us the right units. So if I take frequency, which is per second, and I want to end up with joules, I need to have joules be part of the constant. And I need to get rid of seconds. So I have seconds on top because seconds here is on the bottom, so it'll cancel out. So remember I told you before about constants, how they work, is that a constant is does two things. One, gets rid of the units I don't want, adds the units I do want, and multiplies my answer by a number, kind of my conversion factor, to get it the right size for that, for those numbers that, for those units that I'm using, okay? So it gets rid of the units I don't want, adds the units I do want, and changes the number to the right size for those units. That's what a constant does. No matter what constant it happens to be. So that's what this constant does as well. It gets rid of seconds adds joules and makes the answer the right size. So frequencies are big numbers, and the energy of a photon is really tiny. So we need to have something that has a very small, or a very small decimal number. So that's why it's negative 34. So the photon then is going to be just a particle that's carrying light. Now, the only thing I want you to hear is we didn't destroy the idea of light behaving like waves, because if you remember, we talked about that in physical science. There are some properties that can only be explained by waves. Only be explained by waves. And particles don't do it. But then there's some things can only be explained by particles because waves can't explain it. So we have both. So light has a dual nature. Light has a dual nature. I find it very interesting that you did it long enough until you ruined it. I was just going to wonder how long that was going to take. Remember that God describes himself that God is light, or Jesus says, I am the light of the world. Well, what do we know about Jesus? Did he have a dual nature? Yeah, he was fully God, fully man. But did he ever exhibit them at the same time? Usually not, right? When he walked on water, I mean, that might be a good example of when he probably was doing both. He was fully God, he could walk on water, but he had to walk like a physical. But most of the time he was either exhibiting one or the other. Doing a miracle, that was clearly God, not physical. So the dual nature. And there's a lot of things about light that light is eternal. Because once a light photon has been emitted, it'll go on forever until it's absorbed by something. That's maybe where the analogy kind of falls down a little bit, but it goes on forever. It's eternal. Light, if we remember back in physical science, we said light is self-propagating. It keeps making itself. Isn't that kind of like God? To be eternal, he has to keep making him. I don't know if he actually keeps making himself. He just exists, but he's self-existent. Light is also self-existent. So I find it not just a coincidence that God says that he is light and that Jesus says, I'm the light of the world. That all these things that we've learned about light make that statement a whole lot more meaningful than, he's the light and it keeps me from falling down or tripping over things in the dark. There's a whole lot more to that. The more we find out about God's creation, the more we understand that, there's a lot more to that statement than meets the eye. This would probably be a good place to stop.